So last time we talked about nonlinear equations and nonlinear progression. Maybe it was a little bit. I was told that I was maybe rushing it a little bit. Maybe I should slow down. I feel differently. I feel that I was dragging, but because I don't know or stalling, I would say. Because I don't know your background, mathematical in particular. So for some of you, it could be very simple, easy stuff. For others, it could be a little bit more advanced. So I will try to kind of teach to the middle ground. So if you feel bored, that's okay. Do something else, like check your email. And I will try to do a little bit, maybe a little bit slower. And over the years, I've taught this course. I constantly change it because I never satisfied with it. Numerical method course and subject is very broad, and you cannot really in one class cover everything, or you can cover lots of stuff, but very sketchy. So I'm trying to find this kind of middle ground because I cannot be too detailed, but I want my goal is to give you some idea so that you would be more comfortable with certain concept, especially if you're using models like WRF, for example. I know there is this tendency now to be a modeler by downloading WRF, following instructions, and you're a modeler now, but actually you're not. You're just user of that model. It's like if I'm driving a car, doesn't mean that I'm an engineer now. So I'm trying so that you don't necessarily wrote your own model, but you could understand what WRF does, for example, and maybe change it. Make it better or improve it or make it more specialized and stuff like that. And you definitely need to understand what's going on in WRF, for example, because sometimes people tend to abuse models, using them in an intended way without even realizing it, or they get into this trouble of that model blows up without understanding that they're actually pushing the model a little bit more away from the scope or area that it actually was intended to be used. And models are not forgiving for that. So models always designed for certain range of parameters, and if you put them a little bit away, they may misbehave. So it's important to understand how models actually build and numerical methods that these models employ. So today we're going to start basically more towards like modeling stuff, and modeling is impossible without solving differential equations. So far we've been solving just equations given by some analytical expression like last lecture, when you could actually write the analytical formula and then you just couldn't solve it directly, and you apply your, say, Newton's method to solve it. But the difference with differential equations solutions that we're going to talk about is that unlike differential equation solutions that we're going to talk about in a numerical method, the equations, the nonlinear equations that we considered before, they're usually analytical. So they're given by some analytical functions. So they have all derivatives, you can differentiate them analytically, and then use use a Newton method, you could find solution. But what if you don't have derivatives? Like, what if your function is given not continuously, but as a table? Or what if your function is defined on a certain grid, only in some discrete points, not continuously? How then you're going to solve equations that in your model when there is no continuous field? What we're talking about here is not continuous kind of functions, but discrete functions. defined in certain points that we call grid or lattice. Different sciences prefer different. So basically, we have this discrete values of a function separated in space and in time, and we need to figure out how the system defined in this discrete grid, how it evolves in time according to our equations. And the problem is our equations are written as normal calculus-based differential equations, but there is no calculus here. Computers cannot solve calculus. They don't know what calculus is. Yes, they can compute cosine sine functions, but they cannot actually compute them directly. Actually, there is a program somewhere there, because computers can only multiply, divide, subtract, and add, and that's it. And they just store to memory and get from memory. They cannot do anything else. Everything else is written as a program. It can be hardware kind of based program, or it can be software based program. Like for example, square root of number, it's a program somewhere, or exponential, it's a program somewhere. So computers can only add, divide, multiply. How you teach them calculus? They don't know calculus. And that's the difference that numerical methods represent. We don't solve calculus problems. We solve algebra problems. So we have an ordinary differential equation. That's what, let's start from that. Ordinary means that we have equation something like some functional of, say, of x, some function f, derivative of function f, second derivative of function f, and so on, equals to 0. So before we considered kind of only functional of x equal to 0, but it can be kind of more general equation, and it's called, if you have derivatives, it's called differential equation. It's ordinary differential equation because there is only one variable. As long as you have one free variable, which is x, it's ordinary differential equation. So from that, we cannot do ordinary differential equations on a computer. Computer does not do equations. I mean, the differential, it doesn't know calculus. There is nothing like calculus implemented on a chip. There is no even method for that. All it can do is work with discrete numbers. And space that this formula describes, so our equation is continuous. And our space that computer understands is discrete. It consists of numbers in certain numbers. Moreover, precision of those numbers can be an issue. So you cannot make very, very small, tiny number on a computer because it's limited by smallest number that can be represented on this particular architecture. So you see computers, you need to explain to computers calculus. And that's what numerical methods do. You need to formulate calculus problem in a way that computers understand it, but it's not going to be calculus per se, it's going to be algebra. So you move from ODEs to a discrete system. Discrete problem. So this one is continuous problem. And this is discrete problem. So you're moving from calculus, which is continuous problem, to algebra. All numerical methods is just a bunch of algebra equations. There is no derivative per se. You approximate them with algebra. So instead of derivatives, you move to differences. Or in particular, finite differences. Because there are different differences. There are finite differences, and there are, say, finite volume differences. And those we will consider a little bit later in the course, methods that deal with finite volume differences. So this is very important to understand, that we don't solve calculus, and as a result, calculus rules don't apply here. For example, very simple thing like A chain rule, AB, this is two functional, or let's call the FG, F times G derivative. You know that in calculus, it is F times G prime plus F prime times G, chain rule. This is not true on computers in finite differences. You cannot write this in finite differences. You can artificially make it so. You can artificially make it so using special formulation of your differences, but only for specific rule. If you, like, say, add second derivative, the calculus rule still won't work. So this doesn't work in general. And sometimes people forget about this. So there is always some error. It's kind of approximately true on computer, but there is this error. And what we're trying to do in numerical methods to minimize this error, to make it as if calculus rules apply. And basically, the main reason why calculus does not work on a computer is because in calculus, derivative of a function is defined as a limit of delta x going to 0 of delta f divided by delta x. Right? This is definition of a derivative. But this thing is impossible on a computer. And not because of a precision per se. Of course, you can make it a really very small number on a computer. But the problem is, this is your delta x. It can be like your distance in space between two grid points. You cannot cover, say, region of the United States by 1 micron side difference in grid, like grid. So that from one point to another, it's say 1 micron. It's impossible in terms of memory and performance of computers. So your grid is usually, say, 1 kilometer grid for best kind of one of the best forecasting models. But 1 kilometer is not delta x going to 0. So this is not, so what we go from here, we go just to delta y divided by delta x and make x as small as possible. And so all this, you constantly hear that model resolution has improved. We increased model resolution. It's because as long as you keep increasing model resolution or grid spacing, as your computers become more and more powerful, the goal is to approach this limit, to make it as close as possible to calculus. And then solution, presumably, would look more and more as calculus, and so that your differential equation is actually the actual differential equation, not algebra. So your algebra starts approximating your actual differential equation. So that's the main thing to understand, and that's the main thing to understand the limitations of the models. Because models, again, don't know calculus, they don't solve calculus equations, they solve algebra equations. And that presents very big challenge. So next we're going to use some expressions, and we need some conventions. So usually grid in space is defined. So space, usually variables that are used are x, y, z, for obvious reasons, because many, so space x, y, and z is not usually in your class for, say, for dynamical meteorology and stuff. And time, we usually use variable t. Now, because our space is not continuous, we represent our function only in some points, discrete points. So we use index to count those points. When you program it, so you need some array, and index helps to keep track of those elements. So we use indices for space are I or J or K. I just came from old Fortran, I think, school, or maybe from, because I know that in physics, for example, they often use other letters for indices like R, Q, P, stuff like that. But in Fortran, when it was just created back in the 60s, by default, variables I, J, K, L, M were integer numbers. You didn't have to declare them. They were by default, all variables started from I, J, K, L, M were integer. And all other variables by default were floating point. And I think this is why it came from. So for me, it's very odd to see in the code some index which is like P or Q. And I highly discourage this practice if you use it. Never program with indices other than I, J, K, L, M, N. Because most people actually train to, and it's very difficult to, it just, I don't know, it's, so anyway, just my advice to you, like people would get like really distracted by all this P, Q, A as indices. So for space, we use IJK or MN, whatever. Or no, except for N. N is reserved usually for time. So N index will be for time. And so, let me write it like this. So this goes into X, say K, Y, I, Z, say M, and T will go to time index is written upstairs. So it's a superscript, or what is this one is subscript, and this one is well, upper script. So you have this for time above and for space below. And N is usually reserved for time. Okay, so now, so distance then will be, like for example, if you have grid in X, so you have, say, xk plus 1, and xk minus 1. So this is your points, and the distance between them may not be necessarily the same. They can be pretty arbitrary. So sometimes you may put more resolution or smaller distances between grid points. So those are called grid points. We call them grid points. And these things between them, xk minus xk minus 1, for example, it's grid spacing. Or grid interval. But not generally, I also do that from time to time. This is not resolution of your grid. People sometimes say resolution of my model is 1 kilometer, meaning that the grid spacing is 1 kilometer. Resolution is not the same thing as spacing, because you cannot resolve anything at pixel level. it's like picture of somebody. You need several, quite a few pixels to actually start resolving something, right? If it's face, if you like zoom in into picture into a couple pixels, you cannot say what it is. So similar thing with simulations, you need certain amount of pixels or grid points to resolve something, like cloud, for example, right? So generally, it's in the order of 10 grid points. So you need like from 6 to 10, depending on your methods. But generally, this is what your grid resolution. So if you have grid spacing of 1 kilometer, actually your grid resolution is about 10 kilometers, not 1 kilometer. So you need to make this distinction. Although from time to time, everybody kind of careless about this. But so my resolution of my model is very high. It's 1 kilometer. No, the resolution of your model is 6 kilometers at best. Its grid spacing is 1 kilometer. Okay, so your x, then distance is of course given just by k. This is delta x, k delta x k, where k is from 0 to blah blah blah. Although from 0, usually if I use c, I would use from 0, but in Fortran all indices all array indices start from 1. That's big difference from many other languages, and creates lots of confusion when you rewrite one code to another from written in one language to the code written in another language. So in Fortran, it's usually start from 1. I don't know what's better because in Fortran, you're constantly writing something like k-1 as a result. Maybe C convention is better, I don't know. But because we trying to use Fortran for our problems, we keep this convention. So there are various qualitative properties of numerical algorithms that we let's mention here. So first property, that our algorithm, so properties or properties of numerical algorithms. First, probably most important, one of the most important is conservation. Conservation or conservation laws. So if ODE or PDE or partial differential equation that has partial derivatives satisfy conservation law, so in discrete system maybe that's important because sometimes it's not possible, or just flatly impossible, but you need to strive toward that. So you need to get close as possible. Then maybe discrete system maybe should too. So maybe, like for example, conservation of energy, conservation of momentum. Those are fundamental laws that for fluid, when we're talking about fluid dynamics, they should be probably enforced as close as possible. And we'll talk about some problems that arise when you don't enforce those laws. For example, if you don't enforce conservation of kinetic energy or energy in general in your model is very prone to become unstable, so-called nonlinear unstable, So you satisfy all the stability criterion and your model would blow up anyway. And because you don't, you have this spurious sort of energy in your model because you don't conserve energy. And that spurious source of energy will feed your instability until your model blows up. So we're going to talk about how to enforce some of those important laws, but not all of them. Okay, so next property is positivity, for example. And this is very simple. If your quantity is positive, inherently, physically, like water vapor amount, water vapor content, or concentration of cloud droplets. So if function is greater than 0, when you do something to it with your numerics, it should stay positive, at least. Maybe it may make some weird oscillations, but that's a different story. But it should be positive, because I don't know what physically negative cloud water means. And many models, especially those that use spectral methods like climate models, they do produce lots of negative values for positive quantities like water, but they wrap it under the rug. They basically have fixers everywhere. But that's okay. They're usually small. They don't really do much, and there is nothing you can do about it. You want to be efficient or fast, have fast model, or you want to be very picky about like your what you do. After all, model is always compromise. We create models for specific purpose. If it satisfies that purpose and produces great results, like for example, if you're interested in forecast, and for that you found that conservation of momentum actually makes forecast worse, then don't conserve momentum, because the purpose of your model is to produce accurate forecast. Or don't conserve energy if your forecast is actually better without it. Because it's short, you forecast for relatively short time, so there is no probably problem arising as time goes further. But if it's climate model, conservation of energy is the most important property. You probably agree, because you have what's climate system is just this energy exchange in the system. And if you don't conserve it, you create some spurious sources or sinks of energy. That would be a big problem for your climate forecast. So for climate models, energy conservation is a paramount. And but now recently there is this movement towards universal models. People say this is not right, that some models do outrageous things just because they're good forecasting models. All models should be based on physical laws, not this ad hoc kind of fixers in them. And so now there is this movement to make climate models that they should be also good forecasting models. And it shouldn't be this kind of distinction. So they all should be physically based. And now with more powerful computers, we can actually afford doing that, to use more precise, more accurate numerical methods.
Do you think that will be possible to have forecast models that are also climate models? Do you think it's feasible to have that?
Usually, in our field, there is a separation between climate models and forecasting models. But IFS, for example, also used as a climate forecasting model recently. And but believe it or not, it's not the best one. When it runs as a free model, free run, not subjected to constraint of observations, it doesn't produce very good climate. Doesn't. There are climate models that produce better. I mean today's climate. It's pretty good still, but it's not the best. So best forecasting model, which is IFS in my opinion, is European model. It's not necessarily best climate model. Or climate model, for example, one of the best ones is probably GFDL model. But it's not the best if you like run a prediction of hurricanes. You're not going to make a very good prediction of hurricanes. If you're looking for particular forecasting of hurricanes, not necessarily statistics of hurricanes. say seasonal statistic or something like that. So yes, I think eventually because right now we have this revolution basically happening. We have this transition towards global cloud resolving models. So we basically start resolving big clouds, even running especially for forecasting. It's been done routinely regionally, but now it's actually becoming kind of more, within few years, it's going to be kind of routine forecasting with global resolution of a couple kilometers. The computer technology is not standing still. So I think that in about maybe 20 years, so you probably will see that. I will be probably happily retired somewhere, hopefully. That it's going to be climate forecast using such resolution, like a couple kilometers or so. And weather forecasting models would run like with 100-meter global resolution, something like that. So positivity, nice to enforce, and there are ways of doing that too. 3, reversibility. It means that if original equation can be reversed in time, for example, momentum equation, without diffusion. So like df dt equals to 0, not df, du, velocity equals to pressure gradient. So this equation, if you reverse time, it will produce your initial conditions. So you move forward, then you stop, you reverse time, you will go back to the same condition. Unless there is diffusion. Diffusion is not reversible. So it will, if you reverse this equation, it will blow up. Negative k, impossible. Negative k is needed to reverse diffusion, but it's unstable. Not numerically unstable, it's in principle unstable as a continuous property. So solution does not exist. And so reversibility, it's not very, it's important for actually for forecasting. For say, generating initial conditions for models, they use so-called adjoint analysis, using this kind of adjoint model, running it back in time, some linearized version of the model, because linear equation is actually very nicely reversible, even numerically, when you find differences instead of derivatives. So it's important property, probably not very important for, like, if you're talking about like models that used to study chaotic systems like weather or turbulence, stuff like that. This is not most important property. But anyway, I wanted to mention that. And now, but the very important property is accuracy. So this kind of vague concept, and it's several multi-factor thing. First of all, it's computer precision. Of course, it's important. And the problem, though, so usually people use as highest precision of arithmetics on computer as possible, say double precision, to make it kind of accurate and avoid certain problems by dividing two small numbers and stuff like that. Recently, actually, there's been this trend to reduce precision, which allows you to mimic chaos of a system. So you basically, by adding this artificial truncation error, truncation due to accuracy. For example, usually single precision is 4-byte numbers, floating-point numbers, 4-byte. Some people tried using 2-byte numbers. And in fact, they produce better forecasts, ensemble forecasts. It's been demonstrated that actually it helps to forecast. You create this kind of additional noise, which is actually shakes the system and creates more distinct ensemble members than, so you don't really need the special preparation of your ensemble initial conditions and stuff like that. So this kind of interesting thing. Why people don't like to use double precision per se? They use it, but if given the choice, they wouldn't, because it's expensive. Usually on Intel chips, I would say double precision arithmetic is the same program. You can compile it, say, with -R8 flag. Then all single precision numbers will be automatically converted to double precision numbers. And then you run it. And I've done that before. And my experience was that my model runs about 50% slower just because of that. Why? Because the bandwidth of sending data back and forth increases. You have bigger numbers. Cache is filled much more quicker because numbers again bigger. So there is constant exchange between cache and main memory. And another important thing, if you run on parallel computer using say MPI, your communication of your boundary conditions between different processors, bandwidth also increases. So it takes longer time to just send messages to each other. So that's why people like to compute at single precision as much as possible. So you could, critical portions of your code, say radiation actually requires double precision usually because of very big kind of swings of quantities, very fast, and even smallest errors can actually produce pretty significant, smallest errors in a truncation can produce big errors in a radiation of radiative fluxes. So those you compute with double precision. But say advection and stuff like that, turbulent transport, why you need double? There is nothing, in reality, there is turbulence anyway. There is uncertainty anyway. Why make it double precision? By definition, this process is not precise. It's chaotic. So processes that are chaotic should be computed with single precision, and processes which are require high precision should be computed with high precision, like radiation, for example, or some other chemical, for example, reactions sometimes require double precision, and so on. So that's first thing, computer precision. Then truncation error, and we're going to talk that a little bit. And this truncation error is not related to computer truncation error, representation of numbers, but truncation of representing your calculus by your algebra. So when you do this derivative definition, delta y over delta x, there is no limit enforced. You're kind of trying to make delta x as small as possible, but it's not going to zero. So, and it's causing so-called truncation error. And why truncation? Because this is what we're going to talk about next. It comes from Taylor series expansion. When you truncate it at certain scale, a certain term, and as a result, you produce this truncation error. That's why it's called truncation. So this is error of representation calculus with algebra. And then there are physics errors, very important. And they come not from numerics per se, but from your model of various processes that you put in your model. Like say bulk microphysics. We know that microphysics is very important in clouds, and it's very complex, and you cannot possibly describe the whole thing, the whole system using equations, because even though we know those equations, the problem is we don't know all the data associated with that. For example, concentration of ice nuclei, concentration of CCN, cloud condensation nuclei, their activity, their chemical composition. You don't know all those details, of course. So you're trying to make some kind of educated guess about those, or use some wide brush initial conditions for, say, cloud condensation nuclei, and hope that the exact knowledge of that is not very important for your forecast, let's say. And in many cases, it is not very important indeed. But for example, if you forecast a squall line, your microphysics can be extremely important. With one macrophysics, your score line will die. You switch to another macrophysics, in worse, you have huge number of macrophysical packages. You switch to another macrophysics, and you have very nice forecast. So, but then on a different storm, it can be vice versa, completely opposite. And that's very difficult problem. Then errors associated with radiative transfer. You need to know, even though we know very well radiative transfer in gases, but when you have clouds, there are problems. You need to know cloud fraction. You need to know cloud water correct. Even if you predict it, you produce these errors. So this is what I call physical errors, errors of parameterizations, because you cannot resolve the whole system. You resolve it only kind of using very coarse grid. There are this kind of, not just truncation error, but you need to come up with some kind of parameterization or representation of reality that kind of gets certain aspect of that reality, but not quite. And that produces errors. And of course, boundary conditions and initial conditions errors. And those are tractable problems. They may be relatively simply improved. And with all these observing systems that we currently have, satellite and others, we improving our boundary conditions, initial conditions, like if you're talking about forecast, quite substantially. And that's one of the reasons of improved forecasts over the couple decades, significantly improved forecast. Of course, it's also resolution improved, boundary conditions improved, because you start resolving topography better. That's main reason actually for improving forecast of rain, for example, because topography is very important for generation of storms. And if you resolve them, if you have, instead of like mountains like that, you have one big shallow mountain in your grids, you're not going to predict very accurately some storm.